All right, so this is 2 Part 4 zeros of polynomial functions. And here are some definitions. The rational zero theorem is Descartes' formula to find a list of potential zeros. A lower bound is a lowest possible zero. An upper bound is a highest possible zero. Descartes' rule of signs is a way to analyze the possible positive and negative zeros. The fundamental theorem of algebra says a polynomial of degree n has exactly n complex zeros, including repeated. This isn't the highest tier of the fundamental theorem of algebra. It's its most useful corollary. Every polynomial of degree n can be written as a string of linear factors and irreducible quadratics. That's the linear factorization theorem. And as a consequence of irreducible quadratics, you can have imaginary solutions which only come in pairs. And the pairs look like this: a plus bi and a minus bi. And then if you see irreducible over the reals, that's just one of these quadratics that does not factor. Okay, so the rational zero theorem. This is, again, just like yesterday, best demonstrated through an example. So know that your book has this explanation, but I think it's best learned and taught through an example. So you guys are a funny generation. I've heard you called doomers, but you were born too late to explore the earth, born too soon to explore the galaxy, born just in time to browse dank memes. So not all bad. So let's list all possible rational zeros using the rational zero theorem. Do you remember factor trees in 4th grade? Did you do these? Where you write a number, like 22, and you say that's 2 times 11. Or you write a number 46, and you say, well, that's, I don't know, 46 would be 23 times 2. 23 is a prime, so that doesn't factor beyond that. But anyway, you got to factorize these coefficients. So you're concerned with the coefficient of the leading term, so that's 1, and you're concerned with the constant term, that's 4. So the coefficient of the leading term and the constant term. Those are the 2 values we're going to use to generate our list. So first of all, I write all factors. So the factors of 1 are just plus or minus 1. Those are the things that divide into 1 evenly. And then for 4, that's plus or minus 1, plus or minus 2, and plus or minus 4. That's every number that divides 4 evenly. Every possible factor is what we have to list here. Of course, prime numbers are easy because their only factors are 1 in themselves. Non-prime numbers, it could be a larger list. So once we have this list, we're going to say P is equal to some value from this list of constant factors, and Q is equal to some list of the leading terms coefficients factors. Let me change this to 100. And we're going to now write every possible P over every possible Q. So the denominators are plus or minus 1. You see how that won't change our list? So it's just really P over again. So this is every possible rational zero. Are these certainly zeros? No. They could be zeros. It's a good place to look. And you might wonder, what the heck is the use of that? Well, you have to remember, Descartes lived in the 1600s. Did he have a graphing calculator? Could he, look at a table for a zero? No. He had to investigate the function, evaluate each individual point, looking for a zero. You see what a tedious task this would be, and what an advantage it would be to have a much shorter list to check as opposed to every possible number. So the benefit is largely for ancient times. Now it's more of a curiosity, but it's an interesting fact to know, the rational zero theorem. And also you'll have a test question about it. Yes, ma'am.
So the 1 is called the leading term. What's the 4 called again?
The constant term.
Okay.
So the leading term is the highest power of x.
Okay.
The constant term is the value that has no x attached to it at all. And usually they would be listed first and last. But if somebody wants to throw you a curveball, they might give you a mixed up non-standard form polynomial where they're not exactly in order, and you would rewrite them before you begin this process. So descending order is standard, starting with the highest and then down to the constant.
And what does Q mean?
It's just a variable. It's if you look over here, P over Q, it's just the variable they use. So there's no special meaning for Q. This could be A and B, M and N, X and Y. But Q is every possible denominator of the rational zero. And P is every possible numerator of the rational zero. So again, these are possible denominators, and these are possible numerators. So, and that's kind of confusing. Do you see how the numerators come from the end and the denominators come from the beginning? That is a little counterintuitive. You would maybe expect it to be the other way. So something to make a mental note of. All right, let's do another one of these. So in this one, and actually it says here, determine which, if any, are possible or actual zeros. So let's do that real quick. And we'll leave that part of the question off. So if I go to y equals, clear this out, punch in x cubed minus 3x squared minus 2x plus 4. And I go to my table. I'm concerned about -4 first, not a zero. -2 is not a zero. -1 is not. +1 is. +2 is not. +4 is not. So only +1. So the actual zeros from this list is just +1. Okay, on to the next. So here we see the leading coefficient is 1, and the constant term is -1. So this is going to be a pretty simple list. Our Q value is going to come from plus or minus 1. Our P value is going to come from plus or minus 1. And so P over Q is just plus or minus 1. Every possible rational zero, positive or -1. So let's test these by hand just for fun, shall we? If I use 1 as my special number, and then I'll list the coefficients, and this is something we didn't encounter yesterday because I didn't do every single example. But when you have missing powers of x, do you see how we go from x cubed to x to the first power? We must include a zero placeholder. So include a zero placeholder. So I have 1, 0 for the x squared term, 2, and -1. So I bring down 1, multiply by 1. So is that one a 0? No, because the remainder would be 0. Macy.
I think it's -2.
Is it? Let me look. Oh, thank you. Yes, you're right. Sorry. Okay, so 1, -1. Uh-oh. Still not a 0. Let me double check myself. 1, -1. Okay, yeah, so still not a 0. Same result, slightly different calculation. Let's try -1 now. So what do we think? This one is a 0. And let's just confirm that with the calculator. So I'm getting some kind of blank stares there. X cubed minus 2x minus 1. And go to the table, and we see that -1 is indeed a 0. So that's what our test here bore out. So we'll say that the actual zeros are just -1. And this is every possible 0 here. Stop me if you have any questions. Okay. Okay, so here's one for you. I want you to try to list every possible 0 and then determine which, if any, are actual zeros. Feel free to use your calculator for that second step. And I'll give you a couple minutes here because this is a somewhat lengthy exam. All right. Let's see here. Macy, tell me what the list of possible rational zeros is.
Plus or minus 1, plus or minus 2, and plus or minus 4.
Yeah, similar to that first example we did. And which of these, if any, did you find were actual zeros, Clay?
I have not gotten that far yet.
Okay.
And would you rather us just put it into our calculator and do it quickly, or do it by hand and then check it with the calculator?
As long as you can do it by hand and you're comfortable with that skill, then you can use your calculator.
Okay.
So the only reason to do it by hand would be to cultivate the ability to do so. So if you're already got that squared away, you don't need to worry about it, sir.
I'm going to be -1 and 4.
So Colby says -1 and 4. Let me just double check it, bud. Some people will be a little faster with the calculator than others. And typically that indicates you've used it more. So if we look at our calculator here, -1 is a 0, +4, yeah. I do want to show you again that division because we went through that entire division lesson yesterday and didn't encounter an example with a missing power of x. So this is a good opportunity again because we go from x to the 4th to x squared. So this would be another case where if we were testing one of those, let's test -1, for example. I would put 1, 0, -12, -15, and -4. So this 0 is for a missing power of x. See, we're missing x to the 3rd power. So, and this also must be done in long division. So if you're using long division, you also should include a 0 placeholder for a missing power. So you would put in 0x cubed into your dividend under the house. All right, so bring down the 1, negative 1, negative 1, 1, negative 11, positive 11, negative 4, positive 4, and 0. So don't forget about that 0 placeholder. I wish we would have had an example of that yesterday. All right, so leading coefficient not 1. That's going to complicate our life a little bit. This will be a much larger list. So if I list every possible factor of 15, plus or minus 1, plus or minus 3, plus or minus 15, that I left off 5 here, sorry. Plus or minus 5 and plus or minus 15. Everything that divides 15 without a remainder. And then this 2, plus or minus 1, plus or minus 2. So the numerators are going to come from this. The denominators are going to come from this. So instead of just 1 as our denominator, which doesn't change anything, we now must also consider 2. And that will lead to some redundancies in some cases, but we'll just list everything first. So everything over here divided by 1 is just a list over again. And then everything over here divided by 2. And if I'm going to test these, I'll need to use a different approach with my table. So I'll put the function in like we normally would, 2x cubed minus 5x squared minus 28x plus 15. Double check myself. All right. So if I go to my table, you notice I can't see 1/2, 3/2. So there's one way we can fix that. If I go to my table setup and have the delta go up by 0.5, that's going to allow us to see these half units. So we want to start with negative 15. Not a 0. And then negative 7 over 2, or negative 15 over 2, which is negative 7.5, also not a 0. And then negative 5, not a 0. We'll just keep going here until we find one. There's one. Negative 3. Negative 1/2. I'm sorry, positive 1/2. Negative 3, positive 1/2. And 5. Write those down before I forget them. Doesn't look like we're likely to find another. You see our numbers are getting big again. And there we go. So this is every rational 0. Let me ask you a question though. Is this every possible 0 for this function? So how many total, based on the fundamental theorem of algebra, should we expect it to have? So this was yesterday, you guys. A polynomial of degree n, and also I showed you in the definitions, which was about, 5 minutes ago. A polynomial of degree n has n total solutions. So what is the degree here?
3.
So how many total solutions should we expect?
3.
So should we look for more outside of this list?
No.
No, this is it. This is every 0. Okay. So let's use this skill to solve a polynomial equation. So the water level in a bucket sitting on a patio, and I'm assuming it's raining, can be modeled by, and they give us a function, where f of x is the height of the water in millimeters and x is the time in days. On what day will the water reach, a height of 10 millimeters? So f of x equals x cubed plus 4x squared minus 2x plus 7. And I'm concerned about when f of x equals 10. So this is the polynomial I need to solve. And your first task in solving a polynomial typically is to get one side equal to 0. So in order to do that, I'm going to subtract away 10 here from each side. So I get 0 equals x cubed plus 4x squared minus 2x minus 3. So this is the polynomial I need to solve. And instead of just randomly checking numbers, let's generate a list of rational zeros, possible rational zeros, and see which, if any of those, are actual zeros. So our numerator is going to come from the list plus or minus 1, plus or minus 3. Our denominator will come from a list of plus or minus 1. So those rational zeros are going to be plus or minus 1, plus or minus 3. That's everything here divided by everything here. All right. We could also have grafted and looked for the x-intercept, but that's something that would certainly not have been available to Rene Descartes. He looks quintessentially French. If you ever look up a picture of Rene Descartes, huge nose. That's sort of an essential French look. All right, so let's check our table, and we're worried about plus or minus 1. So we'll start at 0, and we'll go up by 1s this time. So -3 is a no, -1 is a no, 1 is a no, and 3 is a no. Just double check myself here that I didn't make any boo-boos, because you would think this would have a solution.
I might have typed it in wrong, but on my table, I got that 1 was.
I could have missed a click here. Oh, I typed in this, not this. Should be -3 at the end. That's my bad. I didn't type in this latest version. Okay, so there we go. Now let's look at the table. +1 is 0, yes. So the actual 0 from this list, +1. And so after 1 day, the water will be 10 millimeters. Is the end of that.
Okay, so if we solved for zeros for the original equation, would we get 3 that were actual zeros?
So you're talking about up here?
Yes.
So you would get, when the bucket's water level is 0. So there would be 3 zeros here. They could be a combination of real and imaginary. They could all be real. Mathematical models are innately imperfect. So in other words, there is no mathematical equation that perfectly models the natural world. And it's a consequence of some really interesting things, like Heisenberg's uncertainty principle, Gödel's incompleteness theorem. Those two things basically say the universe is unknowable. It rejects modeling. One of the fundamental core properties of our universe is that no mathematical model could ever possibly predict a future event perfectly. You could predict it with an arbitrary degree of accuracy. So the limit could approach 100% accuracy, but you'll never quite get there. So this is an imperfect model, of course, is the point of that argument. And if it had multiple zeros, that wouldn't make sense. So I'm betting it would have one real and two imaginary, but we'd have to experiment with it to be certain. It's a good question. Yes, 3 zeros because it's degree 3. But don't confuse mathematical models with reality. They're always imperfect. All right. So the path of a ball is given by this function, where x is the time in seconds and f of x is the height above the ground in meters. So you see how we would need to solve this, and I'll teach you a little trick here. So this isn't the method that your book would prescribe, but I'll show you how to solve this quickly with a calculator. And I think I showed you this trick once. If you put the left side of the equation in for y1 and the right side in for y2, and then you'll look for an intersection. Make sure your window's big enough. We'll probably need a good bit of y here. It starts at 40. I don't know, let's go to 200. So we want this point. This is negative seconds don't make sense in the context of this problem. So we're going to reject this negative solution. And the positive solution, option 5, if I hit enter, enter, and the guess, the guess was something I glossed over for max and min, but it's important here. I need to get closer to the intersection I'm concerned about, because whichever one I'm closer to, that's the one it will collapse to. So it's about 2.73 seconds. Oh, never mind. Left off an X. My bad. Try it again. I thought it would probably be an integer solution. Second, trace, option 5 again.
Mr. Robert, send Anna to the office, please. Thank you.
Yeah, 5. Sorry about that. Yeah, when I click on this smartboard, sometimes it doesn't detect my clicks, so I'm having to constantly double check myself with the calculator. That's another benefit of you guys following along. You'll often catch any error I make in that respect. So that helps me out considerably. All right, upper and lower bound tests. These aren't super important, but it basically says if you use the synthetic division algorithm with regard to a certain C value on the x-axis, some C, and every number in that last line of division is non-negative and non-positive alternately. So in other words, it goes from positive to negative to positive to negative. The sign switches, or it has a 0. That's a lower bound of the 0. You can't find a 0 below that. If every number in the last line is positive, then that's an upper bound. So you cannot, or it says non-negative, meaning zeros are okay. So if nothing is negative down there, not a single value, then that is an upper bound, a highest possible x. Determine an interval in which all real zeros of this must lie. So if we look here, -2 looks like a 0 to me. And then positive 1, 2, 3, 4, 5, 6 looks like a 0 to me. So let's see if how -2 and 6 behave. So if I do -2 in the division algorithm, 4, 3, 2, 1, 0, no missing powers. So we don't have to worry about our placeholders in this case. So it's positive 12. And 4 plus negative 2 is negative 6. And that's 12, and that's 0. So positive, negative, 0, which is okay. Do you see how this is a valid lower bound by that lower bound test? Alternately non-negative and non-positive. So changes signs or is a 0. That's the criteria is met here. So this is a valid lower. We should not look below that for any zeros, if we won't find them.
So the test is like, it has to be positive and negative for,
Alternately non-positive and non-negative.
Yeah.
So it has to either change signs or be a 0.
okay, and so it passes both.
Mm-hmm.
Okay.
Yeah, so it meets the criteria, which is sort of complex. This is nothing you would ever do in analyzing a problem, probably. Just a curiosity again from the time of Descartes. And now let's check if 6 is a good upper bound. So if it's a good upper bound, I will see no negative values in that last list. And I see no negative values, meaning this is a valid upper bound. So it meets the criteria laid out on that previous page. And so it is a valid lower bound in the case of negative 2 and upper bound in the case of 6. Again, I'm not super wild about these examples. This is not anything that is it particularly useful. Curiosity again. So we'll skip ahead to example 5, which is going to use something called Descartes' rule of signs, which basically tells us the number of positive real zeros is equal to the number of variations in sign of f of x or less by an even number. And this less by an even number is an important concept. Hey, Taya. Come on in. Okay, thanks, honey. Appreciate that. All right. So this less by an even number is an important concept because your answer will be incomplete without considering that less by an even number. And the number of negative real zeros is the same as the number of variations in sign or less by some even number. And notice for negative real zeros, it's f of negative x. So don't worry too much about this. This, as is the case with most things in this chapter, best taught in an example. Okay, so let's describe the possible real zeros of this. And we're going to describe it in terms of positives and negatives. So first of all, I know it has 4 total zeros, including imaginary and repeated zeros and all that stuff, because it is degree 4. So I know it's got 4. And f of x, if I analyze, the sign changes. So I'm looking for places where it goes from positive to negative. So that's a sign change. Negative to negative, that's not. That's a sign change. Negative to positive. Positive to positive, that's not. So you see it has 2 sign changes in f of x. So 2 sign changes. And by that I mean positive or negative. Which means we have 2 or 0 real positive zeros. So this amount or less by an even number. So 2 or 0. Now if I consider f of negative x, so what's going to happen when I plug in negative x? Negative x to an even power will not change anything because negative x squared, for example, is just positive x squared. So negative times a negative is positive. Negative times negative times negative times negative is positive. So if I raise it to any even power, the sign will not be changed. You guys with me on this? So negative x to any even power will just be positive. So it's not going to change the sign of the even terms. It will change the sign of the odd terms. So this changes the sign of the odd powered terms. All right, so x to the fourth does not change signs, but 3x cubed does. Minus 5x squared does not change signs. Minus 2x, this one will change signs because it's x to the first power. One is an odd number. And then plus 7 is also unchanged. So even power stays the same. Odd power changes signs. Even power stays the same. Odd power changes signs. Constant term doesn't count. Just leave it alone. Allie, question? Okay.
I answered the wrong question.
That's okay. Now, we'll analyze this to determine the possible number of negative real zeros. So, no sign change here. Here's a sign change. And then here's a sign change. So, once again, there are two, meaning there are 2 or 0 real negative zeros. So in this case, the important parts of this answer, there are 4 total zeros. There are 2 or 0 real positive zeros. 2 or 0 real negative zeros. So that's the information we've gathered from Descartes' rule of signs. And you might say again, what the heck is the use of that? You just graph it. You would know where the zeros are. You don't have to worry about where they could potentially be. And yes, you're right in that argument. This, again, in our modern day is a curiosity, as is most of the work of Descartes. But it's important to know where you came from, isn't it? That's why we read Shakespeare, Colby, before we read Stephen King. You know, it's important to understand the origins of literature. And many modern authors, in fact, almost all, owe a great debt to the authors of a previous age, as do the mathematicians of this age owe a debt to Descartes, and before him, Euclid, and so on. So important to know where you came from. This is where we came from in algebra. Right, we'll skip ahead to the next example, which relies on the fundamental theorem of algebra. And this is the important corollary. A polynomial of degree n has exactly n zeros. So very important. You've already written that down, but it does bear remembering. And then this linear factorization theorem. We can, if we're using complex coefficients, we can always write a string of linear factors. If we're using only real coefficients, then you will have possibly an irreducible quadratic. So find a polynomial function given at zeros. This is a neat problem. I like this problem. So it says, write a polynomial of least possible degree with real coefficients in standard form that has -1, 2, and 2 minus I as its zeros. And here I give you guys a hint. Complex roots only come in pairs. So if I'm going to write this, I'm going to say P of X. I need to make this little template. And don't fall into this trap, because even though only 3 are listed, we must have 4. We must have 4 zeros, because 2 minus I means 2 plus I also has to be a 0. Complex roots only come in pairs, and they are conjugate pairs. 2 minus I means you must also have 2 plus I. So if I start writing my zeros in here, I get this. So this is the answer But if we wanted to expand it, there are a couple mechanisms at our disposal. We could use Wolfram or Desmos or any of the online calculating mechanisms, or you could just do it by hand, which we'll do real quick here, because it's good for you guys to see some work like that. So first of all, I'm going to multiply these two together. And so that's going to be x squared minus x minus 2. So plus 1x minus 2x gives us that. And then the product of those two is here. And over here, let's simplify this. I'll distribute that negative sign. So we'll multiply these two together. He's just hanging out. So I've got, no, use a bracket here. So I've got x minus 2 plus I times x plus x minus 2 plus I times minus 2 plus x minus 2 plus I times negative I. So distributing the x here, I get x squared minus 2x plus ix. And then over here, minus 2x plus 4 minus 2i. That's 2x plus 4 minus 2i. A lot of this is going to cancel. So this looks really funky right now. But it won't after this next step. Negative ix plus 2i minus I squared. So let's see what cancels here. I get plus 2i and minus 2i, plus ix and minus ix. That might be it. Yep, okay. So x squared minus x minus 2 times x squared minus 4x, if I combine those like terms. So that's this term and this term. And then plus 4. And then minus I squared is also minus a negative 1. So I squared becomes a negative 1. So minus I squared is minus that negative 1. X squared minus x minus 2. X squared minus 4x plus 4 minus a negative 1 is plus 5. So now we're ready to do our last distribution, which is x squared minus x minus 2 times x squared plus x squared minus x minus 2 times negative 4x plus, let me shrink this down so I can fit it all on one line. Go. X squared minus x minus 2 times 5. So that is x to the 4th minus x cubed minus 2x squared minus 4x cubed plus 4x squared plus 8x plus 5x squared minus 5x minus 10. Combining like terms here, x to the 4th. And I like to cross them out when I got a bunch like this. Just kind of helps you keep up. Minus 1x cubed and minus 4x cubed is minus 5x cubed. And then minus 2x squared plus 4x squared plus 5x squared is going to be plus 7x squared. And then 8x minus 5x is plus 3x. then minus 10. And at the end, you can see if you've got everything crossed out. And here we go. So there's the polynomial of least degree that has all those zeros we were originally tasked with. So the alternate method, that's the by hand method. And I know it's a test of your patience to watch a 5-minute math problem. You guys live in the era of YouTube and Vine and TikTok. 30-second videos is about your max attention span. There are alternatives to what you just saw me do. So if I could, Wolfram kind of let us down yesterday. I think we tried to do an example and it gave us a weirdly formatted answer. Sometimes that happens. So it was x minus and then -1 times x minus 2 and then x minus 2 minus I and then x minus 2 plus I. And let's see what he thinks about this. All right, there we go. So if, they don't let you copy paste here because they want you to, they have it formatted as an image. They want you to use their paid version. It's one of the things they lock behind that paid version. But you can always use the snip tool if you want to get a little piece of a page. And if I want to compare it to my answer here, just do this. All right, so questions about that? Okay, so you will see one of those on a quiz or a test. It is often missed, mostly because this calculation is pretty immense. So a lot of attention to detail required here. So every polynomial can be factored to linear and irreducible quadratic factors, which we've already discussed. So let's try to write this as a product of linear and irreducible quadratic factors. So we want every possible factor. You remember we did this yesterday, and division is a tool that will help us here. So what I need to do is find some zeros. Now we aren't Descartes, so we're going to use a little bit of a quicker method. And that is to analyze the graph. X to the 5th plus x to the 4th minus 13x cubed minus 23x squared minus 14x minus 24. I gotta double check here because so often it misses a click. Okay, looks good. So I see 3 zeros here. And let's just go to the table. So -3, -2, and also 4. So we know those are zeros. So what I'm going to do is to divide this by x minus a -3 or x plus 3. And then I'm going to divide it by x minus a -2 or x plus 2. And then I'm going to divide it by x minus 4. So these factors come from this list of zeros. So I'm going to divide it by the things I know are factors. And unless I screwed something up, they should all have a remainder of 0. So we'll start, and we'll do them in order, starting with this one. Then we'll do this one. Then we'll do this one. And the result should be 3 linear factors and 1 irreducible quadratic. All right, so -3 is our special number for this first step here. And then 1, 1, -13, -23, -14, -24. So 1, -3, -2, +6, -7, +21, -2, +6, -8, 24, and 0. You see how that 0 is a good check against arithmetic mistakes? Because if I make one, this probably would not wind up being 0, and I would know it. So now we can rewrite our original function as x plus 3 times, and we started out with a 5th power. Now we're going to go to a 4th power, x to the 4th minus 2x cubed minus 7x squared minus 2x minus 8. So now we're going to divide this by the next one. So this is step 2. And we're using x plus 2. So -2 is our special number. And our coefficients are 1, -2, -7, -2, -8. And so I get 1, -2, -4, 8, 1, -2, -4, +8, and 0. 1, -2, -4, +8, +1, -2, -4, 8, yes. So now I can rewrite it again as x plus 3, and then x plus 2, and then this is to the 3rd power, x cubed minus 4x squared plus x minus 4. We're getting there. One more 0, and that is x minus 4. So in this case, this is step 3 here. 4 is our special number. Our coefficients are 1, -4, 1, and -4. Bring down the 1, 4, 0, 0, 1, 4, 0. And I'm glad we encountered this 0, so let me show you how that would work. We're ready to write it in its final form. So that is x plus 3, x plus 2, x minus 4, and then here, our final irreducible quadratic. This is 1x squared plus 0x plus 1. So again, 3 linear factors, 1 irreducible quadratic factor. Now, if we worked out this problem like Rene Descartes, and I don't know why you'd want to, but let's imagine you do, you would generate a list of possible rational zeros. You would figure out which from that list are actual zeros. You'd get the same list we got by checking the graph on the calculator, and then you would do this. So, question?
Can you make it to where you can see all the work on the page?
That'll be a challenge. I'll try.
Or,
Yeah, that's close to all of it, isn't it?
okay, yeah, that's good.
Yeah, they did an update on this software. Used to, that was so easy. I would hit a certain button and it would do it automatically. But they updated the software and removed that option. Literally something I used 1,000,000 times a day, and they removed it. So I was very frustrated by that fact. Now this is the best you can do, is it won't reduce the size beyond this point. Or if it does, it's really small. But anyway, the auto formatting full page view is dead and gone. So that will be our last example. Any questions about anything we've discussed today? All right, so just to recap, we figured out how to find a list of possible rational zeros and check to see if they are actual zeros. We figured out a way to find an upper and a lower bound for zeros on a polynomial. We figured out how to find a list of possible real and possible real positive and possible real negative zeros using Descartes' rule of signs. And then here, we fully factored a high degree polynomial using all those ideas together, including the division by polynomials we learned yesterday. Any questions about anything? All right, in that case, your mission, should you choose to accept it, is to complete the following. Page 127, 4, 5, 11, 12, and 17. Hope you guys enjoy your big old long 5-day weekend. Oh, yeah, we're off Monday.